Hi, everybody, and thanks for coming to the session. As Patrick said, my name is David Beard. I'm the developer evangelist for Qualcomm Vuforia, which is Qualcomm's mobile vision platform. In today's session, what I'm going to do is provide you with an introduction to Vuforia and talk about our current support for digital eyewear and how that's enabling the creation of a new class of AR/VR hybrid reality experiences. What we've seen is that AR is excellent at providing a transition into immersive experiences for gracefully transitioning a user into an immersive environment, and that it also enables the use of objects as tools within virtual worlds. So I'm going to talk about some use cases for that and show you some examples. And then at the end of the session, I'll take you through a walkthrough of how to author an AR/VR experience in Unity using the Samsung Gear VR. So Vuforia is Qualcomm's mobile vision platform. It's an SDK that enables your apps to see things in the real world and to then interact with them. We've done this by taking very sophisticated computer vision technologies, building them from the ground up for mobile devices, and then providing those to developers with an easy-to-use set of APIs and developer workflows. So any developer can add vision functionality to their apps quickly and easily without needing to know anything about computer vision. Here's some examples of the features and experiences that have been built using Vuforia. Audio. So as I said, Vuforia provides a very simple API. It tells developers what the SDK sees and where that object is in the field of view of the camera. And that enables the developer to accurately render content onto the surface of the object and also relative to it in the environment. So today with Vuforia, we can see a number of things. Firstly, images. We're capable of detecting and tracking flat images, such as publications, print media, magazine covers, and also arrangements of images in a predefined geometry, such as a box or a fan, and also cylinders, which is an image that is wrapped around a constant radius. So we can detect can-like shapes and also cone-like shapes that have surface details on them. We're capable of detecting objects, and these are rigid objects that have a consistent geometry, let's say. There's not a lot of articulating parts, they're not pliable. So it's good for things like toys, appliances, sort of smaller objects that have rich patterns of detail under surface. We can detect text. We provide text recognition for Roman characters. And we can also detect meshes, meaning that we can recognize, detect meshes, which is our smart terrain feature. So before you can look at a table and return the table surface and the props on the table, and it can overlay content on those. It can actually distinguish the table surface from any objects that are sitting on the table, so you can treat them selectively using the app logic in your applications. We provide a variety of SDKs for iOS and Android, and these are in Java, C++, and also Objective-C, and then we provide a Unity extension, which is in C#. So currently we have global adoption. Over 15,000 apps in market, over 175 million installations, and 150,000 developers. It's become truly a global phenomenon. So the primary elements of the platform are the Vuforia engine, a suite of tools that we provide for creating and managing targets, and also for calibrating eyewear, and our cloud services. So the Vuforia engine is really our SDK. And again, this is for phones and tablets, for Android and iOS, and also now for digital eyewear. And that's for Unity and also for Android. So it's Android operating systems, and you can program in Java and also Unity. So we provide 5 SDK versions, 3 of which are for mobile, and 2 of which are currently for digital eyewear. We're supporting Eclipse, Xcode, and also Unity. And then for our tools, we provide a target manager online that enables you to create and manage targets. We're also providing an object scanner, which is an application that you install on your device, and it enables you to capture objects, to basically scan an object, create what's known as an object data file, upload that to the target manager, and then you can embed the database that holds the object in your application, and it supports object recognition. And we're also providing eyewear calibration, and this is an application that you actually install on the device, and it enables you to go through a simple calibration process to personalize the eyewear calibration for each user. Our cloud services are really an image recognition service, so you can query the service from your application, and it returns a target to the app that enables you to track and detect that image in real time. And we provide a web services API that enables you to develop content management systems and gateway applications for your own services that reach into the cloud service and enable you to upload targets and manage targets using a RESTful API. So I'm going to talk about our support for digital eyewear. Vuforia is already used in a wide range of AR experiences today for mobile devices, and now we're enabling these cutting-edge features in a new class of hardware, digital eyewear. Our focus is on binocular displays. Where it's natural for a person to use both eyes and see straight ahead. There are two categories of devices that we support, optical see-through and video see-through. The difference is optical see-through has a transparent lens, and the rendering is actually rendered onto the lens. Any augmentation is displayed on the lens itself. And a video see-through device uses the device camera to capture the world around you, and you're actually looking at the camera image as a video background in the application. It's similar to what a mobile augmented reality app will do, is that it uses the camera image, it lays it into the background of the app, and then you're rendering content on top of that. So currently we're supporting the Epson BT200, which is known as the Movario, and also the ODG-R6, and these are both optical see-through devices. Among video see-through devices, we're supporting the Samsung Gear VR Explorer Edition, and we'll soon be supporting cardboard. So again, the distinction, the Epson and the ODG have transparent lenses. The display is actually rendered onto the lens, and for video see-through, such as the Samsung Gear VR, you're actually looking at the camera video background. You're looking at a video rendering of the camera feed. So there are a number of challenges that we've been addressing to support digital eyewear. Firstly is user calibration, and this is for optical see-through devices. Now the significant thing here is it provides for accurate static registration of content on a target. Everybody's facial geometry is a little bit different. So when you're using a see-through, an optical see-through device, what you want to do is go through a calibration process that ensures that the application knows what the correct transformation of the content for the geometry of your face is, and that's really personalized to the user. It takes into account things like the distance between your eyes, the bridge of your nose, the setting of your ears, so that when you're putting on the device, you consistently have accurate registration for that device. And in the future, this is going to be addressed by eye tracking, and this is pupillary eye tracking, where you'll have cameras that basically watch your pupils, and as you move them, it can accurately correct for differences in the vergence of your pupils and the orientation of them, basically. The other thing that we're addressing, and this is really specific to Snapdragon, is dynamic registration, which is minimizing the motion to photon latency of the rendering. What this means is that as you're moving, what we're doing is optimizing the rendering path so that as quickly as possible, you're going to receive updates of the rendered content on the real world. And also this supports high performance tracking. So these are really optimizations that are coming in from the hardware level. And then we're addressing power and thermal constraints on devices. If you've ever worked with an ODG or the Movario, you know that as you're rendering, as you're processing camera frames, they tend to get very hot, and so we're working on that problem very hard to really optimize as much as possible the power consumption and really the thermal performance of the device. Now, I'd like to discuss the types of AR, VR experiences and use cases that Vuforia enables. So in the hybrid reality case, what this means is that you're using augmented reality and virtual reality complementarily. So they're really two sides of the same coin. You're using AR to gracefully transition into a VR experience. You're not just throwing somebody into VR. And we've seen this to be a very popular case. I'm going to show you some examples of how people are using it. But especially for users who aren't familiar with VR, it's a nice way to take them into put them into a situation that they're familiar with, they can see the world around them, they're comfortable, and then you move them into VR without just slapping it on their face and changing their environment dramatically. You're really using AR as a portal into VR experiences, and you're using it to blend real and virtual worlds. And what this means is that using the target types that we've created, you can create a mixed reality experience. You can bring physical objects into the setting and then use them as tools and devices in a virtual or an immersive world. And this enables you to interact in VR so that you can take, if you notice the image, you can take a physical target, something that Vuforia can detect and track, and then give it a significance in the virtual world so that it can act as a type of tool or a device or a controller. So I'm going to show you some examples. Many of you remember the classic Viewmaster toy with its slides and clicking mechanism. It uses a phone today that you pop into the viewer, and the discs are used to provide an AR experience that transitions the user into a VR experience. So again, as you can see, what's happening there is that the kid has the Viewmaster discs. Those are basically image targets, the ones I talked about at the beginning. When he looks at them, there are a series of models that are presented, and using what's known as gaze detection, he's selecting which experience he wants to go into. Each model represents a different VR experience. So he puts the Viewmaster on his face, looks down, and basically what's happening is gaze detection is able to understand. It's a technique that's able to understand really where the focus of the user's attention is on something, so that you can use that as a sort of interactive device to activate things, to launch interactions. So the next one is Cordiorly. And this is it's a construction project around the Paris airport in the Cordiorly district. There's a train station there. So what they've done is they've taken the building plans and they've turned those into targets. And this experience basically is a dual mode. It starts with a handheld device, right? The user selects which of the rooms in the building plan they want to view, and then they actually slip it into a harness, into a headset, and they use that for VR. So rather than starting with the harness on their face, they're starting with a handheld device, and then they're slipping that into the headset. So I'll show you this. So we've seen two examples here. Basically, the first one starts where the user is wearing the headset, they start in an AR mode, and then they transition into VR. With this, the AR mode is actually handheld, the AR phase of the experience, and they transition to VR by slipping it in. They've made a selection of which content they want to see, they slip the device into the harness, and then they start their VR experience. This next one is Peronio, and it's a pop-up book. And they've taken a different take on it. They actually start in virtual reality. You select which game you're going to play, and then they transition to an AR experience where you're going to play the game, and really the interactive mode of that uses gaze detection again. And what you'll see is gaze detection is very popular. It's something that across the range of the cardboards and the VR ones and the gears and such, you have different interactive modalities. There's different inputs you can use, but one of the consistent ones, if you want to build a portable app, is to use gaze, because it can be applied consistently across these various devices. So let's look at Peronio. So what you've seen there, we actually had 3 different devices. The first one was the Zeiss VR1. The first one was actually cardboard in the Mattel Viewmaster. The second was the VR1, and this third was again a cardboard based. So you'll notice these are all Vuforia applications that are portable across these different, contexts. So you've seen the kinds of hybrid AR/VR experiences that developers are creating using Vuforia. Now I'm going to show you how these apps were developed. The workflow that I'm going to show you was broken really into 5 steps. The first would be that I'll import Vuforia and Oculus into my project. I'm not going to do that for this, but that would be the first step that you need to do in order to set up the project. Then I'm going to configure a scene for augmented reality. Then I'm going to enable that scene for digital eyewear using the Vuforia APIs. Then I'll add Oculus to the Vuforia camera through an integration step. And then I'm going to implement some app logic for the AR/VR transition. So really, the innovation here is that we're taking augmented reality and we're modifying the Oculus extension so that you can gracefully transition between AR and VR. And the significance there is that Vuforia provides a vision-based tracking, and Oculus is providing inertial rotational tracking. Each of those have their own camera, and the camera has a pose on the scene. It's the perspective it takes. The trick is to have a way that you can take the vision-based tracking, hand that off to rotational tracking without disrupting the scene, and then to reciprocally pass from a VR rotational tracking into a visual tracking, and again, so that it's seamless, so it's graceful for the user. So I'm going to go into the Unity environment. Give me 1 second. Can you see that? Okay. So for those of you who aren't necessarily familiar with Unity, let me just give you a quick rundown. Unity is an authoring environment. It's primarily used for game development, and so a lot of it is drag and drop, and you're basically configuring things in what's known as an inspector, which is on the right-hand side here, and that gives you the properties and the options for applying settings to things in the scene. And then the way that you often customize something is by writing a script and adding that script as what's known as a component. So what you're looking at here is a scene view. This is the content, and this is from a game called Reign of a Mirror, which was developed by Qualcomm's Advanced Content Group. So it's a game scene that I brought in, and what I'd like to do is adapt it for augmented reality, then adapt it for digital eyewear, and then make it so that it can work on the Oculus Gear VR, and that I can have AR and VR experiences using this game scene in the Oculus context. So the first thing that I would do is import the Vuforia Unity extension. You'd go to developer.vuforia.com. We're going to be using the digital eyewear capability. That's currently in beta. So go to the download sections, go to beta, and you'll see a Unity extension for digital eyewear. We'll also want to bring in the Oculus Unity extension. That's from the Oculus developer site. I've already brought both of these into the environment, so we don't have to watch me do that. But what Vuforia is going to add to the project here is the Qualcomm Augmented Reality folder. Now, all of our features are encapsulated into a set of easy-to-use prefabs. You'll notice there are image targets, cylinder targets, our cloud recognition service. So when you want to apply functionality to the scene, you're really bringing the prefab into it, and then you're configuring it in the inspector. So the 2 critical prefabs to use for this scene will be the AR camera. That's a special augmented reality camera that we provide that supports augmented reality functionality in the scene. And we're going to be using an image target. So I drag that in as well. Now, to define a target in the scene, let me show you this. I would create one online in the target manager. So this is the target manager. You can upload targets here. You can define databases. It provides really a creation and management tool for targets. So I'd simply select my target database after defining which target I'd want to use. And I'd import that into the scene, and that's going to be added here to the streaming assets Qualcomm Augmented Reality folder. You can see that. So to configure the scene, I'm going to have the AR camera load this database, and then I'm going to configure this image target to use the image that I'd like to use for the scene. So you do that in here. Notice again, here's the inspector on the right-hand side. What I'm going to do, the first thing actually is I have to apply a license key. All Vuforia applications use a license key that unlocks the features of the SDK. So I've already defined one. You would do that in the license manager online. Add that here. Now, to configure my database, I go to the dataset load behavior. And you'll notice there's a checkbox with the name of my database next to it. I select to load that, and then because I want it to be immediately accessible to the SDK when the app launches, I'm going to choose to activate it at build time. The significance of this is that you can programmatically load and activate databases using the API to have a variety of databases in a single app. For this, it's very simple, so I'm just going to do this at authoring time. And now on the image target, I do something similar. Go to the dataset, select the database I want to use, and then select the specific target I want to use, which is going to be the Reign of Amira version 3. Now you'll notice the target is much larger than the content, and we don't want the content to be very small in the target. So I'm going to go back and redefine the size of the target here. So what's going to happen when this target is rendered, when the augmentation is rendered, it's actually going to cover the surface area of the target. It'll be larger than the target. What this relationship means here is the target basically is what's going to be detected by the SDK, and it's going to be tracked in the field of view of the camera. So if I want digital content to be rendered on the target, I simply make it a child of the target in the scene, like this. So what you're looking at here, let me take on, oops, excuse me, is the Reign of Amir game scene augmenting an image target, right? So this is really all you need to do to create a basic AR scene for a mobile device, right? You're adding an AR camera, you're configuring a database, you're adding a target, you're configuring the target for the specific image that you want to use in the case of an image target. And any content that you want to render, you simply make that a child of the target. So when the target is detected, the content will be rendered. As the target moves, the content will actually follow the target in the field of view of the camera. Now, I'm going to configure this for digital eyewear. We have a very simple authoring workflow for doing this. You'll notice on the cue card behavior, there's a button that says switch to stereo camera. Now let me show you something. Currently, for a mono camera mode, there's a single camera that's the child of the AR camera. When I select to switch to stereo camera, it's going to add another camera. And what that means is that it's going to support stereo rendering, really for a binocular experience. Each camera represents one eye. And we've configured those so that they converge like the human eye does, and it gives you that natural binocular see-through type of experience using digital eyewear. So when I do this, you'll notice that I now have a stereo camera left and a stereo camera right. There are a number of configuration options here. One thing to keep in mind, and it's important to know, is that what we're able to do using our digital eyewear APIs is that we actually configure them dynamically at runtime for a device. So we're setting things like pupillary distance, we're setting the skew of the camera projection matrix, we're setting the clipping planes properly. You can customize that, but typically we recommend that you use our default settings, and we let us do that for you, basically. So now this is set up so that it can achieve stereo rendering. What I'm going to do is our SDK will automatically detect whether the Oculus extension is present in a project, and it'll provide you this easy option here, which is to enable Oculus integration. So you don't have to do this manually. It's really a one-step process that if you want to support Oculus in the project, you click on this. And you'll notice what's happened here is that it's added a number of script components to extend the AR camera. And these control the initialization of the Oculus tracker and also the Oculus camera. And they have their own settings, but we're not going to modify anything. What I am going to do is, because we want the Vuforia AR camera and the Oculus camera to be friendly, to get along with each other, that what we'll do is actually create a relationship here so that the Oculus camera follows the AR camera. The significant thing, earlier when I was talking about the challenge of being able to transition from AR to VR and how that's accomplished, this is one of the steps. What you want to do is, because you have two cameras in the scene, you need them to be compatible. You need one to govern the other so that when you're making transitions, they have the same orientation. They're looking at the same things in the scene. And that's how you avoid them jumping or spinning into different orientations. So what I'm going to do here, you'll notice that there is a follow orientation. Let me find it right here. And what this means is that the Oculus camera is going to follow whatever transform, whatever vector position is provided. So I'm going to make the AR camera effectively the governor or the parent of the Oculus camera. And that's really primarily it for the Oculus integration. What we've done, and there's a documentation online, is there are a few simple code changes that need to be applied to the Oculus extension that enables it to be to go in and out of rotational tracking, that enables you to dynamically disable and enable the rotational tracking of Oculus. So you'll see here, our modifications create a new option, which is to enable rotational tracking or to disable rotational tracking. We're going to be doing that programmatically via the API, but that's really what we've needed to do to Oculus in order to make it work with Vuforia, to enable us to transition from rotational into a visual-based tracking. And what that enables, again, is this hybrid AR/VR experience, that you can be in the same scene, you can be using vision for augmented reality, and then you can transition into a virtual reality environment, really within the same game scene. And again, the significance here is that we're able to gracefully hand off the pose of either camera to each other, and to also go into an immersive environment and effectively turn off the video background for AR. The difference, again, what we're doing within a video see-through is we're taking the camera image, we're actually laying that behind the app. So when we go into VR, we don't want to see the camera image anymore. And that's what some of these modifications enable, is that you two dynamically transition between the both of those. So I've done this in AppLogic. We have, again, there's a document at developer.vuforia.com. If you go search Gear VR, you'll see that there's an integration guide that you can use. And then I've developed some AppLogic here that's going to handle the behavior that we want. How do we want to activate this transition, right? So let me just find my folder. Here we go. So there are a few things. One is that I want to be able to toggle between AR and VR. So I've defined a behavior. I'm adding this to the AR camera. What this does is that it's going to recognize when certain interactions take place that indicate that the user wants to go into a different phase of the experience. And so what it's really doing is using that option, is it's selectively enabling or disabling the rotational tracking of Oculus so that it enables the visual tracking to take over. So that's known as the toggle AR VR script, right? The way that I'm going to activate this is using, like the other applications, gaze detection. So I have a script here that what it's doing is looking at the Oculus VR camera, which provides a handy sort of utility function that enables you to raycast from really the center of perspective of the cameras. Now what this means is we have a binocular display, we know that the eyes converge at a certain distance, and what we're estimating really is the center point to sort of make an approximation of where is the user looking, right? And it creates a very natural interface for interacting either in AR or VR. So this is, again, the gaze script is what it's doing. I'm going to add it to the AR camera. Is it's basically looking to determine when is the user looking at the very top of the tower here. So what I've defined is a sort of button in the scene. And when you go in here, you can see there's a little yellow ball at the top. That's what's known as a collider. And really within a physics engine, a collider is something that knows when it's being interacted with. It knows when it's being touched. So the Oculus VR camera is casting a beam out of the center perspective of the lenses, and it knows the collider is going to know, it's going to trigger an event when the beam is looking at it, essentially. So that event, what I'm doing within the script here, is really looking to see when that occurs, and then using that as a simple indication that, oh, we're going to transition now into another phase of this. So again, we're using gaze detection. We're using a behavior that is enabling and disabling the rotational tracking, and it's also modifying the mode that you're in. So basically, the application has an understanding that, okay, now I should be rendering for VR and I should be using rotational tracking versus, oh, I should now be rendering for AR and I'll be using vision tracking from the Vuforia SDK. The other thing I've done is to create a custom event handler. The way that Vuforia works, and really a lot of Unity programming, is it's event-driven. You have behaviors that are defined for certain components of the scene, and you register event handlers with those so that as the state of the behavior changes, it propagates events into these event handlers, and that's how you can customize really the interactive behavior of your scene. So what I'm going to do here is add an image target trackable event handler. And again, this is a custom event handler. If you know a little bit about Vuforia development, what we're really doing when something is detected is in the Unity environment, we're going through the various rendering components that are on these 3D objects, and we're deactivating and activating selectively based on whether they're being detected or if they've been lost. So for VR, the significant thing is that when you've lost the target, you don't want to stop rendering something, because what this means is you're actually now away from the target and you're looking around in the VR world. So you want the content to still be available. It still needs to be rendered for the user. So what we're really doing here is modifying some of Vuforia's event handling behavior so that it won't de-render the target when you're no longer it won't de-render the content when you no longer see the target. Now I should be able to, let me show you what this will look like. Give me 1 second. All right. So this is the target we're using. Again, it's from the Reign of Amiram. I'm going to go into what's known as Vuforia Play Mode, and it's a simulator that we provide for Unity. And this is going to enable us to get a look at what the scene looks like in binocular in the Unity view. Oculus doesn't provide a simulator, so I'm only going to be able to show you the AR phase of this experience. But if you go down to our booth during the exhibition, we're presenting a lot of the AR, VR demos that I'd shown in these videos, and you can get a look at what a sophisticated AR, VR experience looks like. One second. So now this is the binocular view. This is a stereoscopic rendering. You'll notice here that there's a bit of distortion. See that? That's what's known as a barrel shader. I mean it's a barrel shader. Essentially what it's doing is it's correcting for the lens distortion in the Oculus Gear VR unit, so it gives you a full wraparound view of your environment, basically. Now when I go down to the target, this is what you'd see in the Gear VR unit. And then again, when I look at the tower, it's recognizing that there's an event that should be pushing me into a VR mode. Again, there's no simulator for this, so I'm just showing you the AR portion of this. So again, to recap, really the steps here are that we're bringing Vuforia and Oculus into the same project, and then we're adapting that project for augmented reality using the Vuforia SDK. We're then enabling it for digital eyewear by configuring the project for stereo rendering, for stereoscoping. And then we're integrating the Oculus SDK. And Oculus, again, is providing rotational tracking, and it's providing a barrel distortion shader that corrects for the distortion of the gear. If you've ever seen the Gear unit, there's 2 lenses that are used. So this provides you that sort of wraparound view. And then we're making a few modifications to the Oculus extension. Those are documented at developer.vuforia.com in the library. And there's about four code changes that you need to make. And then we're basically providing a capability to selectively enable and disable rotational tracking from Oculus, and we're making a modification to Vuforia's event handling that prevents the content from being de-rendered if the target's lost, so that Oculus can then take over and you have a proper VR experience. So that's it. It's actually, most of this workflow can be accomplished through authoring. There's a bit of coding, but you'll see that it's actually pretty simple. It's achieving a pretty sophisticated experience, but it doesn't take a lot of hard programming work to do it. So that's it. Are there any questions? Let me get this. Oops, sorry.
Okay, here. Why don't you take that mic for questions?
Okay, let me get this. Hold on a second, let me get this out of the way.
So while David's taking questions, we're going to set up for the next speaker. And we're going to stay here for the next session for Dev, but then after the break, Dev is going to move across the hall to the original room it was scheduled for. But stay here if you want to stay in the Dev track. Stay here for the next session, but after the break and for the rest of the conference, it'll be across the hall. Okay.
David, what's the cost of using the SDK?
It's basically, the SDK is free. You can use the SDK for free with a rendered watermark. There's a variety of plans that are available, such as the classic plan that's a one-off fee per app. And then we also provide plans for cloud recognition. So you can develop using Vuforia for free without needing to pay anything. Once you go to launch the app into app stores, and if you don't want to use a watermark, you would purchase a plan for that.
I was wondering if you could say something about the status of smart terrain and whether or not you intend to disclose the SLAM features further.
I don't know what statements we're going to make about smart terrain as far as SLAM. I mean, I think you know that there's SLAM capabilities in smart terrain. But we tend to refer, what we do with smart terrain is we want to simplify it for the developer, so we don't tend to go into the hard, the plumbing of it.
But at this point, as far as I can tell, you're still requiring like sort of like a three-stage process, including like first mapping it out. And then trying
Yeah, it's the thing is, in using smart terrain with a monocular camera, is there really does need to be a user behavior that initializes and sort of bootstraps that. Looking at other hardware that may have a better depth sensing capability, we can reduce that, requirement. But yeah, for the time being, smart terrain is going to need, monocular smart terrain is going to need a user action, sure. Oh.
Hi, why don't you support desktop platforms such as Windows, and do you plan to support them one day?
The support we provide for Windows currently is through the simulator. You can't deploy Windows desktop applications, but you can certainly prototype on Windows. Really, our focus is on mobile devices and on digital eyewear. We're not really looking at desktop apps at this time. Oh, we are evaluating. My boss just told me we're evaluating.
I have a question here. I was wondering if you have any plans for support on embedded Linux?
That I know of, not currently. We're evaluating this too?
No, not available.
Yeah. In the back? So we've seen a number of things. You want, oh, I'm sorry. She's asking what sort of triggers we're using to go between AR and VR. So what kind of interactions we're using for that. Typically, what we've been seeing is a lot of people are using what I'm referring to as gaze detection. It's sort of a term of art in the area. What that means is that they're having the user actually focus on something, and if they maintain their attention on that object in the scene for a certain period of time, they regard that as an indication that there's a selection of something. So it's what people are looking at. But you can also, we provide interactions through what are known as virtual buttons, which is really to know an area of the target that's being touched by the user. That's another good way to do it. And also some of these devices, like the Gear, actually have a touchpad on the side. So we've seen people using that. With Google Cardboard, they have that little slider, and they're using the magnet, and they're triggering that off a magnetic interaction.
David, over here. David.
Oh, one sec. Sorry. Oh, I got two. The guy in the back here.
The question is, do you see a lot of performance differences between smartphones and the type of glasses that you run on, like different specs of the camera, different superpowers?
Yeah, that's one of the things, and you notice in the slide that one of the areas that we're addressing, for instance, is thermal, really the thermal performance of something. So there do tend to be. I mean, they vary across mobile devices as well, but as far as the quality of camera and also the runtime performance of the embedded systems on certain digital eyewear versus what's available on certain smartphones, there does tend to be a difference. Yeah.
David, this will have to be the last question.
Oh, okay.
All right. Do you have any examples of AR, VR transitions for industrial applications? Anything that you've worked on so far? Any use cases? That
As
you're
far as
looking
our
into?
developers, we've seen, the closest I've seen so far is Cordiorly. There are a lot of people that are working on this kind of thing, so I think it's something that's going to be popular. I know that there are parties like Index that are working in the industrial space with AR. I wouldn't be surprised if they do something. But it's a good question. It's something to keep an eye on. Yeah. Yeah, that's exactly it. That's where we've seen a lot of it, especially not even necessarily the VR aspect, but in digital eyewear itself is something that can be brought into industrial space for training applications. Yeah. Thank you.
Thank